Imagine for a second that you're standing inside a modern data center.
Right.
And, if your reference point is from 10, maybe 15 years ago, you're probably picturing a very specific kind of environment.
Yeah, that classic pristine IT closet vibe.
Exactly, like a quiet, heavily air-conditioned room. You have those blinking green and blue lights everywhere.
Hmm.
There's this gentle, almost, I don't know, soothing hum of the server fans.
And it's always freezing.
Yes. You always need to wear a sweater because they keep it so aggressively chilly in there.
Right.
Well, we want you to take that image, that quiet room, and just completely erase it from your mind.
Because it is absolutely not like that anymore.
Not at all. I mean, if you walk into a modern facility today, specifically one that's built for these massive artificial intelligence workloads, you are stepping into something entirely different.
It's a completely different beast.
It is. Picture a massive, roaring, incredibly hot engine. It is this physical, visceral, almost violent environment.
Yeah, violent is actually a really good word for it.
Right. Because of the sheer acoustic volume of the industrial fans, it's just deafening. You can literally feel the heat radiating off the racks, just pressing right up against you.
You're not looking at an IT closet anymore. You are looking at heavy industrial infrastructure.
Exactly. This isn't just a room of computers passively sitting there. It is a heavy industrial plant that's keeping, everything from your daily banking transactions to those generative AI tools you use completely afloat.
And, the transition you're describing from that quiet, chilly room to the roaring engine, it's really the visual and auditory manifestation of a massive crisis. Yeah, a total crisis. Because the infrastructure keeping our digital world alive is under immense physical and financial pressure right now. We have officially crossed this threshold where managing a data center is, it's no longer just about the software.
Right.
Having the most elegant algorithm or the fastest code, it's completely irrelevant if the physical machine running it literally melts itself down.
Wow. Yeah, that's a good point.
We are dealing with fundamental issues of thermodynamics here. Energy consumption, thermal density.
It's all physical stuff now.
Exactly. The staggering cost of just keeping these systems cooled and powered has basically become the bottleneck for human technological progress.
Which is exactly why you, the listener, should care about this.
Absolutely.
Because the ceiling of what we can achieve digitally, the next big leap in AI or medical research or global logistics, it's now being dictated entirely by the physical realities of power and cooling.
Yep.
Okay, so let's unpack this. We've been looking at the absolute chaos happening inside modern AI data centers lately, and we're specifically focusing on the architecture of a platform called SuperCloud Composer, or SCC.
Right, the Supermicro platform.
Exactly. It's a unified management platform. And the mission of our deep dive today is to really understand how this software attempts to act as the central brain, trying to tame this thermodynamic chaos.
Which is no small task.
No, it's not. We want to figure out how anyone manages AI, high-performance computing, and these massive liquid-cooled data centers without losing their mind or, literally burning down the building.
Well, it requires a complete paradigm shift in how we view hardware in the first place.
How do you mean?
Well, we're transitioning out of this multi-decade era where hardware was rigid. It was siloed. It was isolated. Think about how a traditional enterprise handled its infrastructure, right? You had a dedicated networking team.
Right, the guys who just look at routers.
Exactly. They only looked at routers and switches. Then you had a storage team managing the hard drives. You had a compute team managing the servers.
Yeah.
And then, completely separate from all of them, usually sitting in a different building.
Oh, the facilities guys.
Right. You had the facilities management people who only worried about the power grid and the air conditioning.
Like the building maintenance, basically.
Exactly. But what we are seeing now is that the old siloed model is completely dead. It's gone.
It just doesn't work anymore.
It can't. To run these modern, ultra-dense workloads, the entire facility has to work together, from the microscopic silicon chip all the way out to the literal physical water pipes running through the concrete walls.
Wow.
It all has to be operated as a single, fluid, and highly observable ecosystem. You just can no longer separate the IT from the facility.
Man. Okay, let's start with why those traditional data centers are breaking. And I mean breaking both physically and economically, right?
Oh, absolutely.
Because we are seeing these environments under just severe pressure to reduce costs while at the exact same time, scaling across wildly diverse workloads.
Why?
I mean, a single facility might be asked to host, standard traditional enterprise database stuff right alongside massive bursty AI training runs.
In that breaking point, it almost always comes down to a metric called PUE.
PUE, okay, power usage effective.
Exactly. Power usage effectiveness. For anyone who manages a data center, PUE is like, it's the ultimate scorecard.
Right.
It is a ratio of how much total energy a data center uses compared to the energy that actually makes it a computing equipment.
Okay, so total building power versus actual computer power.
Exactly. In a perfect, impossible world, that ratio is 1.0.
Meaning no wasted energy.
Right. Every single watt of power coming off the grid goes directly into doing math.
This should never happen.
And never. Because you have lights, you have cooling, you have power loss in the wires. But the traditional models are failing specifically because they rely on those fragmented tools and rigid configurations we just talked about.
Okay, right. The siloed teams.
Yes. When you can't dynamically control your cooling based on the exact second-by-second needs of your servers, what do? You end up overcooling the room just to be safe.
Oh, so you blast the AC everywhere because you don't know exactly where the hotspots are.
Exactly. And that wasted energy leads to a rising PUE.
Ah, I see.
It also leads to physical footprint expansion. Because if you can't cool them efficiently, you have to physically spread the server racks further apart so they don't just bake each other with their exhaust heat.
Right, and spreading things out means you're building bigger buildings.
Exactly.
You're buying more land, you have to run longer cables. I mean, the operational costs must just skyrocket.
Yeah, absolutely skyrocket. It's a full-blown thermal crisis right now.
Yeah.
In the old days, an IT leader, they worried about software licenses and compute cycles. Their budget was relatively predictable.
Right, you buy Microsoft Office and you buy a server.
Exactly. But now,
Yeah.
responsibility for cost control has expanded heavily into energy and cooling, and those are no longer fixed costs.
They fluctuate.
They are highly variable. When you have these ultra-dense environments packed with GPUs, the power consumption fluctuates wildly based on what the computers are actually doing at that exact microsecond.
That makes sense.
To understand the physics of why this is happening, you have to look at the TDP, the thermal design power.
Okay, what is that exactly?
It's basically the maximum amount of heat generated by a computer chip that the cooling system is physically required to dissipate.
Okay.
For years, a high-end CPU might have a TDP of, say, 100 or maybe 150 watts.
Which is like a bright light bulb.
Exactly. But today, we are seeing AI GPUs pushing 700, 800, even over 1,000 watts per chip.
Oh my God, per chip.
Per chip. And you are packing 8 of those into a single server case.
Wow.
And then you're stacking 40 of those servers into a single rack.
That is insane.
It is. As those TDP levels spike to these unprecedented levels just to handle the AI workloads, the old way of cooling simply hits a thermodynamic wall.
The air conditioning just can't keep up.
Right. Pumping chilled air through a room is becoming dangerously inefficient. Air simply does not have the heat capacity to carry that much thermal energy away fast enough.
It makes me think of trying to cool a volcanic eruption with a plastic desk fan.
Yes, that's exactly it.
I mean, you can point the fan at the lava all you want. You can turn the fan up to its absolute highest setting, but the physics of heat transfer just don't add up.
The heat transfer coefficient of air is just too weak for that much energy.
Right. So are we basically saying that the absolute physical limits of the hardware, like the literal melting point of silicon, are now forcing a complete rewrite of how we architect the management software?
That is precisely the foundational shift taking place right now. The software has to change because the physical infrastructure has fundamentally changed.
Wow.
To move beyond your desk fan analogy, you have to move to liquid cooling.
Right. Water.
Water or specialized dielectric coolant. Because liquid is exponentially better at capturing and moving heat than air is.
Because it's denser.
It's denser, it absorbs heat faster, and it carries it away much more efficiently.
Yeah.
But bringing liquid cooling into a data center introduces entirely new, hypercritical components into your IT environment.
Like what? What changes?
Well, you suddenly have CDUs, or coolant distribution units. You have them at the rack level, literally pushing fluid to the individual servers. And then you have massive facility-level CDUs exchanging that heat with the outside world.
Like the cooling towers.
Exactly. And you have servers with cold plates bolted directly onto the silicon. They call them direct-to-liquid cooled servers.
Oh.
So this isn't just passive plumbing anymore. It is active, dynamic IT infrastructure.
And it requires constant telemetry, doesn't it? I mean, if a fan fails in a traditional air-cooled server, the server gets hot and it maybe slows down its processing speed to protect itself.
Right, thermal throttling.
Yeah, thermal throttling. And an alarm goes off. You have time to react. A guy can walk over there and look at it.
Right.
But if a pump fails and the coolant stops flowing to a modern, 100 kilowatt AI rack, you don't have minutes.
You have seconds.
Right, you have seconds before a catastrophic thermal event just destroys millions of dollars of hardware.
Which means human operators cannot manually monitor this.
You can't just have a guy walking around with a clipboard.
Exactly. You cannot have a technician running around a 100,000 square foot facility checking pressure gauges on water pipes. The operational control has to be automated, millisecond by millisecond.
Which brings us directly to how you orchestrate all this chaos. The industry loves this buzzword, right? Single pane of glass.
They love that phrase.
But SuperCloud Composer seems to be applying that concept with extreme literalness here. They are really trying to unify everything.
They are. Because SuperCloud Composer, it's architected to span multiple generations of infrastructure.
Okay.
It isn't just a shiny dashboard for the brand new liquid-cooled AI racks.
So it does the old stuff too.
Exactly. It's designed to manage your traditional compute nodes, your storage arrays, your network switches, and the physical rack infrastructure, the power and the cooling, all from one centralized interface.
It forces all that facility data and the IT data into the exact same brain. But underneath that dashboard, how is it actually talking to all these different machines? Because historically, a Dell server, an HP server, and a Supermicro server, they don't speak the same language.
No, historically they definitely do not.
Right. But the architecture here relies heavily on something called Redfish. It's described in the source as a standard northbound RESTful API.
Yes.
Can we break down why this specific API standard is such a massive revolution for the person actually building and managing these data centers?
Absolutely. The Redfish standard is arguably one of the most important developments in modern infrastructure in the last decade.
Really? Why is that?
Because historically, server management was deeply, stubbornly proprietary.
Oh, right. Everyone had their own ecosystem.
Exactly. Every single hardware vendor had their own closed-loop system.
Yeah.
They had their own custom dashboard, their own secret proprietary protocol to talk to the baseboard management controllers inside their servers.
So if you bought one brand of server, you were essentially stuck using their management tools.
Completely stuck. It created massive vendor lock-in.
So if I buy servers from 3 different companies for 3 different projects, historically I'd need 3 different dashboards to manage them.
Yes. 3 dashboards, 3 logins, 3 systems to update.
And my automation scripts would have to be written in 3 completely different languages.
It was a nightmare.
So is this Redfish standard basically acting like a universal remote control for the entire data center?
Universal remote control is a great way to look at it, but it's even more powerful than that because it's an open industry standard.
Okay. Who runs it?
It's managed by the Distributed Management Task Force, or the DMTF.
The MTF, got it.
Instead of proprietary code, Redfish uses standard web protocols, specifically RESTful APIs.
Wait, RESTful APIs? Like what websites use?
Exactly. It communicates using the exact same JIT, PT, and POST requests that your web browser uses to talk to a normal website.
Oh, wow. That makes it so much easier.
It really does.
Yeah.
By using Redfish, SCC ensures that the platform can integrate, monitor, and automate actions on any compliant hardware.
Yeah.
You aren't locked into a proprietary silo anymore. It's essentially a universal translator.
That is huge. And the documentation for SCC also heavily emphasizes open API support and Swagger-based documentation.
Yes.
And for the non-developers listening, Swagger is basically a tool that reads the API and automatically generates a beautiful interactive manual for it.
Right.
It means developers don't have to guess how to talk to the data center, right? They can look at the Swagger docs and immediately write their own Python scripts to automate tasks.
Exactly.
It makes the physical heavy metal infrastructure as easily programmable as like a virtual machine in the cloud.
And that programmability is the ultimate goal. But there's a catch.
Okay, what's the catch?
If you make the physical infrastructure that programmable, and you centralize the control of everything from the AI algorithms to the literal water valves,
Right.
the management software itself has to be absolutely bulletproof.
Right, because if it goes down, everything goes down.
Exactly.
Let's talk about that resilience then, because SCC can be deployed as a virtual appliance, or you can install it directly on bare metal Linux servers.
Correct.
And it's backed by a distributed Kubernetes architecture. Now, Kubernetes is usually associated with keeping web apps running, right? But here it's being used for automatic failover of the management brain itself.
Yeah, it's a brilliant use of it. Kubernetes essentially abstracts the software from the hardware it runs on.
Okay.
So if you deploy SCC across a cluster of management servers using Kubernetes, the system is constantly checking its own pulse.
It's monitoring itself.
Right. If the specific physical server that is running the main instance of SCC loses power or, catches fire,
God forbid.
the Kubernetes architecture detects that failure immediately, and it instantly spins up a new instance of the management software on a healthy server.
So the brain is distributed and self-healing.
Exactly.
Okay, that covers hardware failure. But I have to push back on the core philosophy here for a second. Because if you unify literally everything, compute, storage, network, and the physical cooling pipes into one single pane of glass, aren't we just building the ultimate catastrophic single point of failure?
That's a fair question.
I mean, think about the security implications. One compromised password, one successful phishing attack against a tired administrator, and a hacker doesn't just steal data anymore. They can turn off the cooling pumps and physically melt the entire data center.
It is absolutely the most critical question you can ask when discussing unified infrastructure, because centralized control inherently creates a centralized target.
Exactly.
But the architecture of SCC approaches this through incredibly strict multi-layered identity and access management.
Okay, how does that work?
Well, first, it integrates with enterprise identity providers, federated systems like Keycloak, Active Directory, and LDAP.
So it hooks into the overarching security policies a company already uses.
Right.
It leverages their existing multi-factor authentication and all their conditional access rules.
Yes. You aren't creating a separate, weaker password just for the data center management. It ties into the strong corporate identity.
Okay, that makes sense.
However, relying purely on centralized authentication introduces its own risk.
How so?
Think about it.
Hmm.
If the network goes down and SCC cannot reach the Active Directory server to verify your password, you cannot be locked out of the system that controls the cooling for your melting GPUs just because the network hiccuped.
Oh, wow. Yeah, you need a way in.
That is why SCC maintains a highly secure local administrative fallback. It's basically the break glass in case of emergency account.
Right.
It operates entirely independently of the network identity providers.
Gotcha. But even if the authentication is secure, what happens when an authorized user just makes a mistake?
Human error.
Yeah. What prevents the networking guy from, accidentally clicking the wrong button and turning off the water?
That is where role-based access control, or RBAC, becomes the ultimate defense mechanism.
RBAC. Okay.
RBAC ensures that a user's permissions are strictly scoped to their exact job function.
Right.
So the network administrator logging into SCC, they will see the switches, the port configurations, the routing tables.
Well, not the water.
Right. They will physically not see, nor will they have the API permissions to interact with the coolant distribution unit.
So it's invisible to them.
Entirely. And the storage administrator can provision hard drives all day, but they cannot adjust the CPU power limits.
So the single pane of glass isn't actually a single view for everyone.
Oh.
It's more like a dynamically generated pane of glass customized to your specific security clearance.
Exactly. And the real argument here is that this unified approach actually improves overall security by removing blind spots.
Blind spots?
Yeah, think about it. Supermicro supports hardware architectures spanning over 30 years.
Oh.
If you rely on fragmented legacy tools, you inevitably have fragmented security. You have these orphan servers running outdated firmware that literally no one monitors because, well, somebody lost the login to that specific legacy dashboard 5 years ago.
Right, the forgotten server under a desk somewhere.
Exactly.
Yeah.
Centralizing the management through SCC allows a security team to enforce global governance. They can patch vulnerabilities across tens of thousands of nodes simultaneously.
That's super powerful.
It ensures there are no invisible vulnerabilities hiding in the dark corners of the facility.
Okay, so we've established how the software is built to be resilient, how it translates the hardware's language using Redfish, and how it locks down access so nobody accidentally triggers a meltdown.
Right.
Now, let's look at what it's actually monitoring on a granular level, because we need to talk about the physical reality of liquid cooling. We're talking about telemetry, leaks, and lifelines.
And this is really the intersection where the digital commands meet physical plumbing. And we need to be clear about this. Liquid cooling in a modern AI data center is not just passive copper pipes holding static water.
Like a radiator in an old house.
Right, it's not that.
Yeah.
It is a highly dynamic, highly pressurized, actively managed thermal transfer system.
Okay.
SEC is architected to integrate deeply with the entire cooling topology. We are talking about integrating with in-rack cooling loops, in-row cooling units, and rear-door heat exchangers, or RDHX.
Okay, let's explain RDHX for a second for everyone.
Sure.
Instead of pushing cold air through the entire room like we used to, an RDHX basically replaces the back door of the server rack with what is essentially a massive radiator.
Right.
The hot air exhausts from the servers, it passes immediately through this liquid-filled radiator door, and it's cooled down before it ever enters the ambient room.
Exactly. It contains the heat at the source.
It's so smart. And SEC is managing these along with sidecar coolers and all the way out to the massive cooling tower sitting on the roof of the building.
And the telemetry they're pulling from these systems, specifically from the coolant distribution units, is incredibly dense.
What kind of data are they pulling?
Well, SCC isn't just checking if the power is on. It is constantly measuring the exact flow rate of the coolant in liters per minute.
Wow.
It is monitoring the pressure differential across the pumps to detect clogs or cavitations.
Cavitations?
Yeah, air bubbles in the fluid that can damage the pumps. And it is measuring the precise supply and return temperatures of the fluid. Furthermore, it maps the complex dependencies of the entire cooling loop.
Why does mapping the dependency matter so much? I mean, why not just monitor each part individually?
Because a failure at one point cascades downward instantly.
Okay.
If a primary pump fails in the facility-level CDU out in the yard, it immediately stars the rack-level CDUs inside the building of chilled water.
Oh, man.
And then those rack CDUs cannot absorb the heat from the liquid-cooled servers in that specific row. SCC understands this entire hierarchy.
But let's state the obvious physical fear here. The water. For anyone who has ever, spilled a cup of coffee on their laptop, the idea of pumping hundreds of gallons of pressurized water inches away from high-voltage, multi-million-dollar GPU clusters is terrifying.
It is.
Water and electricity are mortal enemies.
It is the absolute nightmare scenario for any facility operator. Because a catastrophic leak doesn't just destroy the hardware it touches.
Right.
It can arc, it can start electrical fires, and it can take down the entire power grid of the building.
Which costs millions.
Tens of millions.
Yeah.
That is exactly why the leak detection capabilities integrated into SCC are arguably its most critical feature. The platform utilizes policy-driven leak actions.
Policy-driven is the key phrase there.
Yeah.
Because it's not just a moisture sensor detecting a drop of water, turning on a red light, and sending a passive email alert to a technician who might be on their lunch break or stuck in traffic.
Passive alerts are useless when dealing with high-density liquid cooling. Useless.
By the time they read it, it's too late.
By the time a human reads the email, the rack is completely destroyed. SCC allows administrators to define autonomous protective actions based on the severity and the location of the leak.
Okay, let's walk through the exact microsecond timeline of a leak event.
Okay, let's do it.
So, a seal fails on a cold plate attached to an NVIDIA GPU.
Right.
Fluid starts pooling inside the chassis. What actually happens?
Okay, so the rope sensor at the bottom of the chassis detects the change in resistance caused by the fluid.
The water touches the rope.
Exactly. It sends an immediate interrupt to the server's baseboard management controller.
Okay.
That controller instantly relays the alert to SCC via Redfish.
The API we talked about?
Yes. SCC receives this telemetry and immediately evaluates its predefined policy for that server.
How fast?
Within milliseconds.
Oh.
SCC can autonomously enforce a multi-step containment protocol. First, it might instruct the orchestrator to immediately migrate the AI workload running on that specific server to a healthy node in a different rack.
Oh, to save the math.
Yeah.
To preserve the computation.
Exactly. You don't want to lose the workload. Second, it sends a command to the power distribution unit to instantly drop all electrical power to that specific chassis.
Just cut the power dead.
Cut it, eliminating the risk of a short circuit or an electrical fire. Finally, it can signal the rack-level CDU to close the specific localized valves feeding that server.
Oh, physically shutting the pipe off?
Yes, it physically isolates the coolant flow and prevents any further spillage. And all of this happens autonomously.
No humans involved.
Zero human intervention, ensuring that the rest of the multi-million-dollar AI infrastructure maintains its reliability and uptime.
It's literally the data center equivalent of autonomous self-preservation.
It is.
It's like it sacrifices the limb to save the body.
Exactly right.
And notice that in your timeline, the second step was cutting the power. Because alongside all that cooling telemetry, SCC is managing power via the PDUs, the power distribution units,
Mhm.
with just an incredible level of granularity.
The power awareness is foundational to the whole system. It tracks the AB power feeds constantly.
What's AB?
In enterprise environments, every server has at least two power supplies, and they're plugged into two completely separate electrical grids, feed A and feed B.
Just in case one fails.
Exactly. SEC constantly validates that both feeds are active, ensuring your redundancy is actually real, not just theoretical.
Because sometimes people unplug things by accident.
Exactly. It monitors the massive utility feed ingress, tracking the raw megawatts or kilovolt amperes literally entering the physical building from the local power company.
And it maps that power path all the way down, right? From the megawatt utility drop outside, through the switchgear, through the uninterruptible power supplies, all the way down to the exact individual electrical outlet on the rack PDU.
Correct. It provides complete end-to-end topological map of where every single watt is flowing.
Man, to put this in perspective for you listening, let's expand on like a smart home analogy.
I like this one.
Right, imagine your home thermostat, but instead of just looking at the ambient air temperature in your hallway, this system is tied into your entire electrical panel. It knows exactly which element on your kitchen stove is starting to overheat.
Right.
It sees a massive voltage spike coming down the power lines from the street outside. And it autonomously throws the specific circuit breaker for your refrigerator before this surge can start an electrical fire.
And it leaves the rest of the house alone.
Exactly. All while keeping the lights on in the rest of the house. Now, take that level of predictive, mapped intelligence and scale it up to a multi-megawatt data center spanning 3 football fields.
It's wild.
That is the level of control SCC is executing.
It perfectly illustrates the shift we are discussing. We have moved from passive monitoring, just, watching the dials on the dashboard, to active, policy-driven, autonomous control over the physical environment.
But managing a single rack or a row this way, handling a leak or a power surge locally, that is one thing.
Yes.
The real world of AI operates on a much, much grander scale. When we hear about these massive tech companies building new data centers, they aren't talking about a few racks here and there.
Oh.
They are talking about warehouse-scale AI deployments. Tens of thousands of GPUs working on a single problem. How does SCC handle that scale without the management network itself buckling under the weight of all that telemetry?
Well, SEC is architected to scale seamlessly, from a small edge deployment all the way up to multi-site, full-scale data centers. But for the heaviest, most demanding AI training environments, the platform features a dedicated module called the AI Supercluster.
The AI supercluster.
Yes, this module is purpose-built because managing 10,000 GPUs is fundamentally different than managing 10,000 standard web servers.
Right, because 10,000 web servers are usually doing 10,000 independent tasks. They don't care about each other. They're serving 10,000 different web pages.
Exactly. But an AI supercluster is generally working on one massive monolithic mathematical problem, like training a large language model.
Like GPT or something.
Exactly. And because they're working on the exact same problem, they require continuous microscopic synchronization. The AI supercluster module allows administrators to manage this massive distributed physical architecture as a single unified entity. You aren't managing thousands of individual servers anymore.
You are managing the supercluster as one thing.
Yes.
The interface they provide for this sounds incredibly futuristic, actually. As an operator, you are looking at a visualization that abstracts away the sheet metal entirely.
Yeah, you don't even see the boxes.
You can visualize the compute trays containing the processors, you can see the power shelves feeding them DC voltage, and most importantly, you can visualize the fabric.
The networking fabric.
Right, the NVLink switches. And NVLink is that high-speed proprietary networking that connects NVIDIA GPUs together, allowing them to share memory and act almost like one giant building-sized chip.
But to manage a system acting like a building-sized chip, you need unprecedented visibility into the internal workings of the silicon itself. And this brings us to the performance metrics module.
Okay, let's get into that.
When you are operating an AI supercluster, checking the ambient temperature of the server case from the outside is practically useless.
It's too slow.
Way too slow. SEC utilizes Prometheus-compatible exporters to pull what is known as in-band telemetry.
Okay, we need to clearly define the difference between out-of-band and in-band telemetry because it's super crucial here.
Yes, it is.
Out-of-band management is what we've traditionally used forever, right? It relies on a separate, tiny computer inside the server, the baseboard management controller, to check physical sensors.
Right.
So if out-of-band is like a doctor putting a hand on your forehead to see if you have a fever,
Right.
what is in-band telemetry?
If out-of-band is feeling for a fever, in-band telemetry is like having microscopic sensors floating in your bloodstream, broadcasting your exact cellular metabolic rate in real time.
Whoa, that's a huge difference.
It is. In-band telemetry means the management software is talking directly to the operating system and the silicon itself. It's pulling data straight from the processors while they're actively executing code.
But wait, let me be deeply skeptical here for a second.
Go for it.
Doesn't pulling data directly from the chip every single microsecond use up compute power?
That's a good question.
I mean, if I am constantly asking the GPU for its temperature and its voltage, aren't we stealing processing cycles from the AI workload itself? Aren't we degrading the performance of the system just to monitor it?
It is a classic engineering trade-off.
Yeah.
It's the observer effect in computing.
Right.
Yes, running monitoring agents on the host operating system does consume a fraction of CPU and memory resources. You are paying a small tax.
Okay, so it does slow it down a tiny bit.
A tiny bit. However, in modern AI clusters, the cost of not having that granular visibility is catastrophic failure.
Which is way worse than losing a fraction of a percent of performance.
Exactly. Furthermore, the industry has developed highly optimized low-overhead exporters to minimize this tax as much as possible. And what's fascinating here is that SCC is designed to be entirely vendor-agnostic in how it pulls this data. It doesn't rely on a proprietary monitoring agent that only works with one specific brand.
Right. It integrates with the primary telemetry engines
Yeah.
from all the major silicon players.
Yeah.
Like, it hooks into NVIDIA via their data center GPU manager or DCGM.
Correct.
If you are running AMD accelerators, it integrates using the Radeon Open Compute Platform, ROCm. And if you are using Intel hardware, it utilizes one API.
So regardless of whose silicon is doing the math, SCC is pulling incredibly deep metrics. It pulls per GPU thermal telemetry.
Per GPU?
Yes, meaning it knows the temperature of every individual chip in a rack of hundreds of chips.
That's wild.
It monitors the PCIe I/O throughput, which measures exactly how fast data is moving in and out of the processor. It tracks the clock analytics, showing if a chip is throttling its speed to prevent overheating.
And all of this microscopic real-time data is fed into time series databases like Prometheus and visualized in these really nice Grafana-style dashboards.
Right, very visual.
The interface plots these live temperature readings against threshold alert bands. You can visually see a specific GPU creeping toward its thermal limit. But I want to explore the why here.
Okay, the why.
Why do we need this level of microsecond in-band telemetry for an AI cluster? I mean, why is this fundamentally different from monitoring a massive traditional enterprise database? Say, the servers running the global payroll for a Fortune 500 company.
It comes down to the fundamental thermodynamic signature of the workload itself.
The signature.
Yes, how it uses power. A traditional enterprise database, even a really massive one, is relatively predictable. Transactions come in, they're processed, and the power draw is somewhat steady. It fluctuates, sure, but it looks like rolling hills on a graph.
Okay, smooth rolling hills.
Right. But training a massive AI model, it operates in violent, intense bursts.
Violent bursts.
It looks like a heart monitor during a cardiac event. When an AI training run moves to a new epoch, or it processes a new massive batch of matrix multiplications, tens of thousands of GPUs can simultaneously spin up from idle to 100% maximum utilization in a fraction of a second.
Oh, wow. So we're talking going from a relatively low power draw to suddenly pulling megawatts of power and instantly generating massive amounts of heat in milliseconds.
Precisely. The thermal spike is instantaneous. If you rely on out-of-band management, pulling a temperature sensor every few seconds, you entirely miss the spike.
By the time it updates, you're already in trouble.
Exactly. By the time a traditional out-of-band sensor registers that the ambient air in the chassis is getting warm, the silicon itself could already be suffering from localized thermal events.
What does that mean?
Microscopic hotspots that physically degrade the chip. Or they cause the high-speed network fabric to drop packets, which corrupts the entire multi-million-dollar training run.
Oh, so if it gets too hot for a split second, it drops a packet and ruins the math.
Yes. AI requires instant, automated responses to maintain stability. The telemetry loop has to be as fast as the compute cycles themselves.
It's wild to think about the physical forces at play inside these machines. We are building these digital brains that operate with the thermal violence of a combustion engine.
It's a great analogy.
But all this automated AI, the Kubernetes failovers, the liquid cooling policies, it is all amazing in theory.
In theory, yes.
In practice, however, data centers are still physical buildings.
Very much so.
Human beings still have to organize these machines, wheel them off the loading dock, commission them, and update them. There are people walking the floor with screwdrivers and crash carts.
Right, the technicians.
So how does this software actually interface with the messy reality of human operations?
Well, the designers of SEC clearly understand that despite all the automation, data centers are physical spaces operated by human technicians. The platform is designed to model how humans actually think about and logically organize these massive spaces. And it does this primarily through features like pod view and the compute module. These are features built specifically for day 2 operations.
Day 2 meaning everything that happens after the initial installation.
Exactly.
Let's talk about pod view, because when I hear the word pod in a data center context, I usually think of a physical containment structure, right? Like a row of racks enclosed in glass doors to keep the cold air in.
Right, hot aisle containment. But these are logical abstractions.
Ah.
Yes, pod view allows an administrator to break away from the physical constraints of the building. Instead of forcing a human operator to look at a rigid spreadsheet of physical rack locations, like rack A1, rack A2, rack A3 pod view, allows them to group resources logically based on how the business actually uses them.
So you can create a pod based on a specific workload.
Exactly.
You could define a pod that says, these 50 servers, regardless of where they physically sit in the building, are entirely dedicated to the new generative AI project.
Right, or you can group them by tenant if you are a cloud provider hosting different corporate clients.
Oh, that's smart.
You can even create logical pods based on power and cooling boundaries, grouping all the servers attached to one specific water loop.
And this logical organization solves a massive logistical headache during expansion, doesn't it?
It really does.
Because when a new shipment of physical servers is wheeled in off the loading dock, plugged into the power and the network, and powered on for the first time, they don't just disappear into the ether of a massive network anymore.
No, through Redfish and standard discovery protocols, they drop into a centralized discovery pool within SEC.
A holding pen.
Exactly. It makes it incredibly easy for the human operator to see the new hardware, verify its specifications, and literally drag and drop it to assign it to the correct logical pod.
It perfectly bridges the gap between the physical delivery of a 200-pound box of metal and its actual software deployment.
It does.
And once a server is assigned to a pod, you enter the real day 2 operations, managed through the compute module. This is where you handle the entire life cycle of a machine. The documentation outlines bare metal OS provisioning, which includes something called metadata injection for DevOps.
And bare metal provisioning is crucial. When a server arrives, its hard drives are completely blank.
Right, it's just metal.
Historically, someone had to manually install the operating system or, at best, use a really clumsy network boot process.
Yeah.
SEC automates this entirely. But the metadata injection is where it becomes incredibly powerful for modern IT teams.
Let's explain metadata injection using like a kitchen analogy.
Okay, let's hear.
It's not just automating the process of installing Linux on the server. That's like just turning on the oven. Metadata injection is like slipping a highly specific recipe card into the oven before it even turns on.
I love that.
So the exact moment the operating system finishes installing and boots up, it reads that recipe card, reaches out to the network, downloads the specific AI frameworks, configures its own network ports, and instantly starts cooking the exact workload it was intended for.
Without a human ever logging into it.
Exactly.
It's brilliant. It connects the physical hardware provisioning directly into the automated software pipelines, the DevOps pipelines that software engineers use.
It saves so much time.
But the compute module also handles the bane of every infrastructure administrator's existence.
Firmware updates.
Firmware updates.
Oh man, the silent killer of weekends everywhere.
It is the absolute worst.
Yeah.
SEC manages updates for both the BIOS, the fundamental code that wakes a server up, and the BMCs, the baseboard management controllers. And it does this via secure local repositories.
So it downloads it locally first.
Right. When you are managing an environment with tens of thousands of nodes, a new security vulnerability might require a patch to every single motherboard.
Which is terrifying.
Having a unified platform to push a signed, verified firmware patch across a logical pod of 5,000 servers simultaneously without a technician having to manually log into each one, is a massive reduction in operational risk and human error.
Yeah, you just press one button, basically.
Exactly. It also allows for remote bulk power actions, like executing a graceful shutdown of an entire row of racks before a scheduled maintenance window.
But out of all these incredibly high-tech, futuristic features, the Kubernetes self-healing architecture, the millisecond liquid cooling leak containment, the Prometheus exporters pulling telemetry from the silicon, there is one highly specific, very human detail in this architecture that I absolutely love.
I think I know what you're going to say.
The UID light.
The unit identifier. It is perhaps the most critical physical feature on a server.
I just find it amazing you have this multi-site data center managed by an AI orchestrator analyzing thermodynamics in real time, executing complex Redfish RESTful API commands. And sometimes, the absolute most important feature on the entire multi-million-dollar dashboard is a remote button that makes a tiny blue LED light blink on the front of a piece of metal.
It really is.
Because, at the end of the day, there is a human technician standing in a hot aisle. The fan noise is deafening, they're wearing ear protection, and they are staring at a densely packed rack of 40 physically identical servers.
They all look exactly the same.
Right, and they need to swap out a failed memory module, and they need to know exactly which server to pull out of the rack if they pull the wrong one.
They take down a healthy node, which could ruin a training run.
Exactly.
It perfectly validates the comprehensive, grounded nature of the platform's architecture. It demonstrates that the designers understand the full, messy spectrum of data center operations.
Yeah, they get the reality of it.
SEC has to serve two completely different masters. It has to provide the high-level, time series analytics used by C-suite executives for budget planning and capacity forecasting.
The fancy...
Right. But it also has to serve the immediate physical reality of a technician trying to replace a failed FRU, a field replaceable unit. If you have the most advanced AI analytics in the world, but your technician pulls the wrong GPU tray because the software couldn't flash the identification light, your multi-million-dollar management system has failed its most basic physical task.
It is the literal connective tissue between the ethereal cloud and the concrete floor of the facility.
Absolutely. And this focus on day two usability maps directly to the different environments SEC is designed to serve. The architecture highlights three main market deployments.
Okay, what are they?
Well, first you have cloud and hyperscale environments, where the primary focus is on massive automation and ensuring firmware consistency across tens of thousands of identical nodes.
That makes sense.
Then you have enterprise deployments, where SEC provides that unified monitoring, integrating the shiny new AI liquid-cooled racks right alongside the company's traditional legacy IT infrastructure.
The old stuff and the new stuff together.
Exactly. And then you have edge and IoT deployments.
This one is fascinating to me.
Right, because it's the exact opposite of a hyperscale facility.
It's tiny.
Yes. We're talking about maintaining the health, power, and cooling awareness of small clusters of servers placed in geographically dispersed, highly remote locations.
Like a telecom shed at the base of a cell tower, or a server rack inside a dusty manufacturing plant.
Exactly. Places where you might not have a trained IT technician on site at all.
So if something breaks, you're out of luck.
Right. The remote management capabilities, the ability to reset power or flash a BIOS from hundreds of miles away, becomes the absolute only lifeline those servers have.
Wow. Okay, let's bring it all together.
Let's do it.
We are wrapping up our deep dive into the SuperCloud Composer architecture. To summarize what we've covered today, we've looked at how SEC takes the terrifying, unprecedented complexity of modern, liquid-cooled, high-density AI data centers and attempts to distill it into a manageable, highly observable, unified platform. We explored how it translates the fragmented languages of hardware using standard Redfish APIs. We looked at the critical necessity of autonomous, policy-driven leak detection when mixing water and electricity.
The millisecond response.
Right. We discussed the need for microsecond in-band telemetry to manage the violent thermal spikes of AI superclusters. And we grounded it all in the human element, down to the absolute necessity of a blinking UID light for a technician on the floor.
It really covers everything.
It does. Ultimately, this entire platform is about maintaining control in a physical world that is scaling exponentially.
It acts as the foundational operational control plane for the next generation of computing. We simply cannot build the future of artificial intelligence on fragmented legacy air-cooled paradigms. The physical infrastructure must adapt, and the management software must become the central nervous system tying it all together.
So what does this all mean for you? As always, we want to leave you with a final provocative thought to mull over, something to explore on your own that builds on everything we've just discussed today. Think about the historical trajectory of technology we've just mapped out. We as a species have engineered software artificial intelligence that is so incredibly powerful, so mathematically demanding, that it pushes our physical hardware to the absolute brink of physically melting down.
The software is quite literally trying to destroy the hardware it runs on through sheer thermal output.
Exactly. Which in turn requires us to build more software complex orchestration platforms like SEC just to manage the physical cooling pumps, the water pipes, and the electrical grids keeping that hardware alive.
It's a crazy cycle.
It is. As hardware and software become entirely, inextricably codependent for their basic physical survival, we have to ask, will the data centers of the future act less like machines that we turn on and off and more like biological organisms?
Oh, I like that.
Like complex entities that require an intelligent, autonomous, always-on life support system just to survive their own thoughts.
It is a really profound perspective. The data center is no longer just a concrete building housing metal computers. It is evolving into a single, breathing, hypersensitive entity.
It's definitely something to think about the next time you casually open an app and ask an AI to write a polite email to your boss for you.
Right.
You are engaging a massive, roaring, water-cooled organism just to save yourself 5 minutes of typing.
It really puts it in perspective.
It really does. Well, thank you for joining us on this deep dive. Keep questioning the infrastructure that powers your world, both the visible and the invisible. We'll see you next time.